Okay, area of a circle. There we are. Slides! Brilliant. So, hello. I'm going to talk... this is the wrong version, but it doesn't matter. I'm going to talk about some maths. It's maybe seemed trivial to you, but it took us 1.5 months to formalise. So, we were doing the area of a circle, which probably you learnt at school that the area of a circle is pi r squared. But why? You probably were never told at school unless you had a very, very good maths teacher. But we can have a look at the proof and we can decide whether it's formalisable or not. So, many people will and have told me that this is stupidly trivial and it doesn't need to be proved. Many of my teachers at school, when I asked, why does the area of a circle equal pi r squared, they told me, it just does. Accept it and move on with your life. But ignoring people is what I do best, so let's prove it anyways. So, the easiest way to prove that the area of a circle is pi r squared is by taking a circle, then splitting it into segments, and then taking those segments and putting them in a rectangular fashion. Then from this, we can take infinitely small segments, and what we get, instead of this weird bumpy thing you see in front of you now, you get a rectangle. And then, wavy handy mathematics, we get that the area of a circle is pi r squared. You may already see some problems with this proof. But after we've got the area of a circle is pi r squared, we can try and formalise it. So let's formalise this. It's a proof, and okay, it's got a bit of wavy handy mathematics, but we didn't formalise it this way. Why? It's extremely informal. It didn't quite kind of meld itself nicely to going into lean. Some examples is, how do we choose the triangles, or the kind of the segments? How do we then take these triangles, and how do we limit over them? How do we get them infinitesimally small? And last thing, probably most important thing, why can we do the transformation from that circle to that rectangle? All of these facts would have had to be formalised, and we decided that it was going to be a massive pain in the arse. So we decided on the following proof. We're going to define a disk, which was a problem within itself. Then we were to show that the disk is exactly as defined between two functions. Then we can show the disk is like measurable, which I'll explain later. And we're going to show that this meaning that this disk is measurable is the same thing as saying that our result is meaningful, because we can only integrate over this disk if it's measurable. And after that, we show the rather simple and quite nice fact that twice the integral from negative r to r of r squared minus x squared, or rooted dx, is just pi r squared. And then quod erat demonstratum, we have a proof. This seems simple. We had it. At this point, when we were talking to Heather about the problem and our proof, we thought we had got it. We can do the integral quite nicely. All the kind of big machinery is there. Proving that a disk is measurable. Yeah, okay, that may have been slightly annoying, but we could do it. Showing that a disk is slightly defined between two functions is a thing that we didn't quite get through our heads until Heather explained it to us. But what do you mean? To show that we had a disk, we had a circle, a unit circle, and what we had to show was that we had two functions which are plus and minus the square root of r squared minus x squared, and this forms the area between them. Yes, I may have been slightly dyslexic with that line, but we had to show... Yeah, we had to show that it was in between those two, and that was a unit circle. Okay, so we're currently on the proof sketch slide, and we've got these things in front of us. We've got to define a disk and show that that disk is exactly defined between two functions, which means that we've got a positive root and a negative root, and between that is a disk. And then show that it's measurable, which we'll see in a minute, and then do the nice integral, which was I enjoyed that bit, that was the fun bit. And then we had a proof. Most of it was kind of like funny, fiddling with kind of intricacies in analysis, but we won't see the proofs. If you want to look at the proofs, there's a QR code at the end of the slides. Okay, so firstly, defining a circle. The natural way to define a circle is to use a 2D ball. So we'd use the kind of the metric.ball, which is in mathlib, which just defines a ball. And we could have used that, but there were some logistical problems. So we defined a new disk as such, which took in a radius r and then just defined it in the usual way. So it's the points in r by r is less than this radius squared. On the fact of those logistical problems, the problem I found was extremely amusing, because what we found out was that metric.ball was actually a square, not a circle. And so if we were to use metric.ball, we wouldn't be actually finding the area of a circle, and many things would just break. So we had our new definition of a disk, and we moved forward with that. And so now, in mathematics, if you're trying to prove that the area of a circle is pi r squared, you wouldn't have to do any of this preamble stuff. You would just take a circle and you'd say, okay, this is a circle, let's just take this and take the integral from negative r to r of root of r squared negative x squared dx. But we've got to do all this preamble because Lean likes everything laid out in front of it. So now we've got to show that a circle is exactly defined as being the region between negative square root of r squared negative x squared and square root of r squared negative x squared on the open close interval of negative r. So we use this brilliant piece of Lean code called region between, which you've got on the screen there. I'm on the region between slide at this point. So we have f and g, which are functions from alpha to r, and s is a set alpha, and we have a set which is alpha by r. And yes, we did. Yes. Exactly, yeah. We had, yes, R is in. We had some problems with the fundamental theorem of calculus. We had to create a new version of the fundamental theorem of calculus in order for this to work, because we had slight problems with negative R. So all of our lemmas are on an open close interval, because you can do the negative R case separately, which we do in the proof. Which it's the sort of thing that you'd only get in Lean. Yes. Yes. Exactly, yeah. Yeah. They're basically the same thing, inverted commas, because we ignore the upper R actually in the proper region between definition. So we proved this, and I've omitted the proof. It was long, and I didn't want to put proofs in slides because I've been told that is bad practice. So now we've proved that we've got a disk, and the disk is the area between two different functions. And now I'm going to take you on a crash course in measure theory and teach you all I know about measure theory, which isn't much. So I can talk about measure, and probably the first thing that will come into your mind is like a length or an area. I'm sorry to the pure mathematicians here, this is probably going to be very incorrect, but it'll be perfectly fine for what we need it for. So length, area, or something else, they aren't mathematically grounded. So we can consider a more grounded approach, which is called measure theory. And so here's some definitions. They're all about sets, don't worry. I've tried to kind of make them as simple and understandable as possible. We're going to define two objects. A sigma algebra, so we take a set X, and then we define a sigma algebra F that is a non-empty collection of subsets of X, such that the following hold. Firstly, X is an F. Then if A is an F, then the complement of A is an F. And if AN is a sequence of elements of F, then the union of ANs is an F. And they're the three axioms that define a sigma algebra. And I'm aware the first axiom there means that they can be non-empty, but shh. And second definition is a measurable set. So we're going to take F and say that it's the sigma algebra. And A is a subset of X, which is a set. And then A is called measurable if A is an F. So there are two definitions of measurable and sigma algebra. I don't know if you've seen them before, but I hadn't before this. So they may not sit with you perfectly, but basically measure is a bit like length, and it's going to be our way of talking about area. And that's all you need to know. So we can now prove that our disk is measurable. So this proof is the shortest, and it's the best, because we can get to continuity from measurability with a brilliant lemma called continuous dot measurable. And this lemma turns everything into continuous lemmas, and then we can use the amazing tactic called continuity. And that makes this proof so simple, so succinct, and it's very pretty. So here we are in like 3 lines. We have the fact that a disk is a measurable set. So that's measurability, tick. Integration. So we're coming to the end now, not much left. So we've proved that it's measurable, we have a disk defined, all we have to do now is integrate it, get PR squared, and quadrate demonstratum, we have proved it. So next, integration. It's pretty abstract, but we have the fundamental theorem of calculus. So if we can prove that the differential of a function is another function, then we can move backwards, and we have the integral. So we prove the following. We prove that the differential of r squared sine arc sine x on r plus x times the square root of r squared negative x squared is 2 times the square root of r squared negative x squared. I probably should have recorded myself saying that and played that again and again. But if we take this and we can prove this fact, we have the integral that we require. So, firstly, exactly. How else are you supposed to do integration? Fundamental theorem of calculus. Tick. Do it the easiest way, Kevin. There's no point in reinventing the wheel. So, well, we did reinvent the wheel because we had to reinvent the fundamental theorem of calculus to work on an IOC. So, firstly, we let f be that function. And note that lambda x means that we're introducing a variable x that we can use in our function. And then we define big F. We're using the notation that, as we saw before, we've got d by dx of what we call big F, and that's the same as little f. So, yes, well, I actually didn't write this bit of code, so don't blame me. It's got lambdas. Yeah, it is just basic f of x, but you put the x on the right hand side of your colon equals. So we've got these two functions, we define them, and finally we prove that it has derivative f has derivative little f, or 2 times little f defined at x, because that's what this thing here means, is that we're going 2 times f of x, and that's 2 times f of x. And then x is saying we're differentiated with respect to x, and has derivat saying big F has derivative 2 times f of x when defined, or with respect to the little variable x. And that's over an IOO, which is a open at both sides interval. Okay, so we've defined all the stuff we've done. There is a proof after this have. Again, I've omitted it. We don't need to see proofs. They're there. Go look at the code if you want. So we've defined that. So now we have everything we need to prove the fact that the area of a disk, which is written as volume disk r nn real dot pi is equal times r squared. So that's our pi r squared. Yes, I'm getting there. We had a slight problem. When we consider a circle, we have an imaginary bound on our circle, because imagine a circle with a negative radius. What's a circle with a negative radius? It doesn't really make sense. So what we had to do basically was saying, okay, R is going to be a non-negative real. That's what NN real means. It's non-negative. So it can be 0, but it just can't be negative, and that's fine. A circle with radius 0 is just a point. That's fine. We don't care. We just can't have R to be negative because disk R does funny things, and volume disk R does even more funny things, and it doesn't make sense mathematically. So what we've got here is the theorem about the area of a disk. We said that volume, which is the canonical measure that we're considering, and that's going to be area. So volume is our area. So we're saying the area of a disk with radius R, which R is a non-negative real, that's equal to the non-negative real version of pi times by R squared. The non-negative real dot pi is there for the fact that we need the left-hand side to the type check with the right-hand side, and if you used real dot pi, the whole thing would complain at you for the fact that you're getting a non-negative real on the left-hand side, then you're taking a real pi and multiplying it by another non-negative real. So we just needed to use the non-negative real dot pi. Otherwise Lean would have a hissy fit of us and just chuck all its toys out of the pram. And that's the theorem statement that we wanted to prove. The proof went on for, I think it's like 30, 40 lines. Again, I've omitted it. You can go look at the code if you want. So the proof now goes along the lines of, because of the way that volume is defined, we can then say that it suffices to prove the integral of 2 times f of x, which we define back here, a little f of x, which is the square root of r squared negative x squared. The integral of that between negative r and r. Note the funny notation of an integral. For some reason, whoever defined this decided it was an amazing idea to go lower bound dot dot upper bound. And so we're going for x in negative r to r, and then 2 times the square root of r squared negative x squared, all rooted, is equal to the natural non-negative real dot pi times r squared. And this can be proved using Fermat's theorem, fundamental theorem of calculus. Hey! It can be proved using fundamental theorem of calculus and the results from before, which were our h-deriv. And after that, it produces a couple of continuity lemmas, which we can solve with continuity, and we are done. But not without one last cheeky calc block. So the last thing in the proof is you just have to prove that which is x, which is our integral, is the same thing as taking the big F evaluated at r minus big F evaluated at little r. And once you've done that, you have done the proof. It is done. It is finished. Ta-da! Okay, so what have we learnt? Nothing is trivial, first thing. Everything always has to be proved. That's the one big lesson that Lean has taught me. Nothing is trivial. There's always something that has to be proved. There's never something so trivial that you can say, it's simple. I had a similar experience with a Scholze log lemma. He said the whole thing was basically trivial. It took me ages to prove it. There are always intricacies. There are always things where you can look closer at it and you can look in and find things. And the area of a circle is not trivial. It's not a trivial fact. There are some very interesting and kind of rich mathematics behind it all. And that's why it took us 1.5 months to prove. And if somebody ever tells you something is obvious, it isn't to computers. Fin. There's QR codes for the slides and the code.